When I'm talking to very conservative people, I usually say I'm a Marxist because I believe that capitalism is a very exploitative system, that socialism would be a much better system, but we have to figure out how to organize it. And I believe that class struggle is very, very important in any society. On the other hand, if I'm talking to leftists, I want to emphasize all the ways I differ from Marx. So the ones I've just told you are the things that I agree with Marx about. But I disagree with Marx about the labor theory of value. I'm a neoclassical economist in terms of general equilibrium theory and what determines prices. I think they're determined by supply and demand and preferences and technology. So I disagree with Marx about the falling rate of his theory of the falling rate of profit. So for leftists, I want to make distinctions between what I believe or what I think and what Marx thought. So it's not really wrong to call me a Marxist, but I tend not to do that among people that I'm interested in having left-wing conversations to. I want to emphasize the important that, for instance, in economics, I think that using the neoclassical tools of price theory and general equilibrium theory are extremely important for understanding reality. Roman has told me that he's spent some time teaching you the theory that I've developed about optimization that I call Kantian equilibrium. I'm going to there are various versions of this kind of optimization. I'm going to only talk today about the simplest version of it because it's the clearest, it's pedagogically the easiest thing to try to teach you. What's a symmetric game? A symmetric game is a game where all the players are identical except for where they're seated around the table. Think of it that way. They have the same preferences and the same payoffs, just subject to changing the names of people. So if you think of a payoff matrix for a 2x2 game, like the Prisoner's Dilemma or the Stag Hunt or the Battle of the Sexes, these are represented by payoff matrices that are 2x2 symmetric matrices. On the diagonal, players have exactly identical preferences for which profile along the diagonal of the matrix they would like, and the off-diagonal elements are symmetric. So as I said, you've studied a number of these, I think, the Prisoner's Dilemma, the Stag Hunt, and so on. Now, let me give an example of a symmetric game in a production economy that's a lot more complicated than a 2x2 game. Suppose we have a bunch of fishers on a lake, and they all have the same preferences over fish caught and labor expended. They want to catch more fish, and they want to work less, right? So their utility is increasing in fish and decreasing in labor. Very standard utility function. But the more people who fish on the lake, the harder it is to catch a fish, because there are only a finite number of fish in the lake, and there are congestion problems if a lot of people are fishing. The probability that you'll catch a fish goes down if lots of people are working on the lake. So that's a monotone, decreasing game where the contributions of people, I'm going to call the strategy of a person his contribution, that is to say, how much he chooses to fish, the labor that he expends on the lake. And my payoff function is a decreasing function of the, if we all have the same preferences, that's a perfectly symmetric game. That's all I have to say at the moment. Another example is voting. If you take a very simple view of voting, and everybody values the outcome in the same way, then everybody who has your politics, who would like a certain, candidate A to win, they have the same preferences in a very simple model. They get a certain value from the candidate winning, and whether the candidate wins or not depends upon how many people come out to vote with our politics. That's a symmetric game. Another example is signing the Declaration of Independence in the United States, and I'll talk about this example more. The politically active people who were fighting the British or thinking of starting a war against the British to get independence for the United States, were called together to discuss whether they should sign this Declaration of Independence, asserting their freedom from the British. The more other people sign, the better I like the outcome, because the probability of winning independence is going to depend upon the probabilities of everybody signing. So the payoff there are, what's the probability of winning independence, with, however, a certain risk involved in signing the declaration. So there's both a payoff and a positive benefit from signing, and a negative and a positive cost also from signing, the probability that you'll get captured by the British and thrown in jail or hanged. Abstractly, we can represent the payoff function of a person in a symmetric game as a function of the contributions, E1 through En. Think effort, E for effort. Some contribution, it can be money or labor or any kind of positive number. Your contribution is a positive or zero number, and you get a payoff, which is a function of everybody's contribution. Now, in many symmetric games, I mean, an example of a symmetric game, this is a completely general form. These functions can be different for different people. But suppose everybody can write his or her payoff function as a function of his own contribution and then the contributions of all the other people. I mean, that's one way of writing this. But if they have the same function, so my fish caught depends upon how much labor I expend, and let's say the total labor of everybody else. And if we have the same payoffs with respect to those two arguments, that would be an example of a symmetric game. Now, a game is monotone increasing if every player's payoff is increasing in the contributions of the other players. So I'll say it again. I'm not saying anything about how my payoff changes with respect to my own contribution, but I'm saying that in a monotone game, my utility or payoff has to be an increasing function of what everybody else contributes. So what's an example of that game, of a monotone increasing game? It would be building a bridge, producing any kind of public good. So each member of the village has to chip in some money to pay for the bridge. And the more that everybody else chips in, the bigger the bridge is going to be. And that's good for me. With respect to my own contribution, it's a cost for me to contribute. So my utility may not be increasing in my own contribution, but it's certainly increasing in the contributions of others. So building a bridge, production of any public good, is a monotone increasing game. Another example is recycling. So we each have to decide whether to recycle. There's a slight cost to recycling. Nobody observes whether you recycle or not. You do it in your own kitchen. If I value a clean environment, let's suppose everybody values a clean environment, then my payoff is an increasing function of how much other people recycle. So that's a monotone decreasing game. It may be increasing or decreasing in my own recycling. I'm not so concerned about that. Paying taxes is another idea, another example of a monotone increasing game. The more taxes other people pay, the better, because that means we'll have more goods provided by the government, more public goods, more transfer payments, and so on. So that's a monotone increasing game. Now, often people don't think about that. They only think about the cost of their paying taxes themselves. But you really have to think about the fact that, you're paying taxes, maybe a cost to you, maybe significant, but you have to also consider the fact that when everybody else pays taxes, that's very good for you. So there's a labor supply game with taxation in which each worker's utility is an increasing function of the labor supplies of other workers. Because the more other workers contribute, the more they work, the more taxes they pay, and hence the greater will be the value of public goods and transfer payments that I may get. Signing the Declaration of Independence was a very interesting example. Benjamin Franklin was the hero of that meeting. I don't know if you guys have heard of Benjamin Franklin. He was an American founding father, so to speak. And he gave a speech at that meeting. He saw people were hesitant about signing the declaration that had been written. Why? Because when you sign the declaration, it's going to be publicly announced. You signed, it'll be in all the newspapers, and the British are going to maybe come after you. They're going to put out a wanted poster for you. So Franklin gave a speech in which he said the following. He said, if we don't hang together, then most assuredly we will each hang separately. So that expression depends upon the fact that hanging together in English means being solidaristic and working together. So the idea is, and it's a cute phrase because there's a pun on hang, right? The second hang in that statement, we'll all hang separately, is a very different kind of hanging. So he was urging people to sign the Declaration of Independence. That was a monotone increasing game because the more that other people sign, the better it is for me because I value independence. Example of a monotone decreasing game is fishing on the lake. As I said, when fish are scarce in the lake, the more that other people fish, the worse that is for me, because it'll lower my probability of catching a fish. Another example is rubbernecking, the accident in the other lane. You're driving on the highway and there's an accident in the other lane. Everybody slows down to look at the accident, right? And that slows you down. So that's also a monotone decreasing game. The more that others look at the accident, that's their contribution, looking at the accident. The more that other people do that, the worse it is for you. Emitting carbon in the atmosphere is the biggest example today of a monotone decreasing game. I personally, my country, the more carbon that my country emits, it has two effects. It has some effect on the global climate, but if I'm a small country, it might not be much of an effect. Emitting carbon means I can produce more at this point because production requires carbon emissions, as long as we don't have completely non-fossil fuels providing energy. So, but as far as other people are emitting, that's a negative thing for me because it affects the climate of everybody, including me. So the contributions here are climate emissions or carbon emissions, a monotone decreasing game. And I've said what a monotone increasing game is. Now let's remember what a Nash equilibrium is. A Nash equilibrium is a profile of contributions to the game such that no player would desire to alter his contribution given the contributions of others. And this idea is the foundation of non-cooperative game theory. Now here's a very important fact that you may not know. Nash equilibria of monotone games, either monotone increasing or monotone decreasing, it's true for both kinds of monotone games, are almost always Pareto inefficient. Almost always Pareto inefficient. Now this fact has a name when the game is strictly increasing. What is that name? The name for the Pareto inefficiency of a monotone increasing game is the free rider problem. It's got that popular name in popular occurrence. Monotone decreasing games, also the Nash equilibria, are always Pareto inefficient, sorry. Almost always Pareto inefficient.
The tragedy of the commons?
That's the tragedy of the commons, very good. So the tragedy of commons is the name, the popular name for the Pareto inefficiency of monotone decreasing games. And the free rider problem is the popular name for the Pareto inefficiency in monotone increasing games. Those are very, very important problems which afflict, they're often called market failures if you have a market economy. Okay, now how would we model cooperation instead of competition between players? So the Nash equilibrium, players are competing with each other, okay? One proposal is this: a contribution profile in which everybody contributes a certain amount E star of a game is a simple Kantian equilibrium if every player prefers this profile to any other constant contribution profile. So you ask yourself, each person asks himself, suppose we all contribute the same thing. What would I like that thing to be? If everybody answers the same number, that's a simple Kantian equilibrium. I'm talking only about symmetric games now, because everybody will have the same answer to that question in a symmetric game. Everybody has the same answer to that question. There's the same amount of contribution that everybody would like everybody to make. So in words, I've got it in red here, E star is the contribution that each would like all to make. And the reason I call that a simple Kantian equilibrium is that Immanuel Kant's famous ethical position was called the categorical imperative, and it said a person should take the action that he would will be universalized. He should take the action he would like to see universalized. So that's exactly what this is. Now, the big theorem is that the simple Kantian equilibrium of any monotone game is Pareto efficient. So in other words, if people optimized in the Kantian manner, if they asked themselves the Kantian question rather than the Nash question, there would be no tragedy of the commons and there would be no free rider problems. They would all vanish. Well, that would certainly be very nice. That would certainly solve a lot of Pareto inefficiencies in the real world if people are Nash optimizing. So why doesn't everybody think this way? Well, maybe people do a lot of the time. But our non-cooperative game theory does not teach us to look for this behavior. Why? Because it models rationality as Nash optimization. But I say that's a very narrow viewpoint. Nash optimization is a formal model of going it alone. Why? I take the behavior of other people as fixed. I assume they're simply parameters in my own decision problem. I'm the only one who's thinking about the decision. I simply assume other people are fixed. That's going it alone. Whereas Kantian optimization is a formal model of cooperation or solidaristic behavior. Let's look at the prisoner's dilemma. So here's the payoff matrix of a prisoner's dilemma. The row player can play either C or D, and the column player can play either C or D. And if they play CC, they both get 1 unit of utility. If row plays C and column gets D, then row gets -2 units, column gets 3. If they both defect, they get 0, 0. The unique Nash equilibrium of this game is 0, 0. But notice it's Pareto dominated by CC. However, CC is not a Nash equilibrium. Why? Because suppose row plays CC. Then column thinks, well, I can either take this column or this column. If I play C, I get 1. But if I play D, I get 3. So if row player plays the first row, column is going to play the second column. What about if row player plays the second row? Well, then column's choice is between, again, this or this, but 0 is greater than -2. So again, column will play D. And since this is a symmetric matrix, the same argument holds for row. So this is actually something that's stronger than a Nash equilibrium. It's called a dominant strategy equilibrium. Okay, no matter what the other fellow does, the best strategy for me is D. So Nash players are caught here. What do Kantian players do? They simply say, if we were both to play the same thing, what would I prefer? Would I prefer we both play C? Or would I prefer we both play D? Well, I'd prefer we both play C because I get a utility of 1, which is bigger than 0. And column will reason the same way. So if they ask that question, what is the strategy I'd like both of us to play? They'll agree this. That's the simple Kantian equilibrium. And as you see, it's Pareto efficient. It can't be dominated by any of these other choices. Why doesn't everybody do this? Why in the prisoner's dilemma doesn't everybody, they just cooperate and play CC? Because row, what happens if row plays C? Then column, if he doesn't want to cooperate, can do better by playing D, because 3 is better than 1, is bigger than 1. And then Rho says, well, if he's going to do that, I'm going to get screwed. I'm going to get -2. But if I play D and he plays D, I'll get 0, which is bigger than -2. So that's how, if you don't trust the other player to cooperate, then you'll decide not to be a Kantian player. So that's the key thing. Rho must trust Column to cooperate, to make cooperation a good choice for him. That's the key problem. Is there enough trust among the players of the game that they will agree not to play Nash against other players, but to cooperate with other players? Suppose we feel solidarity with other people. We have an experience of acting in concert to solve problems. Perhaps I think you and I are very similar. We grew up in the same culture. I reason whatever I end up deciding to do in the prisoner's dilemma, you're going to come to the same conclusion. Therefore, I need only ask, on the main diagonal of the payoff matrix, what profile do I prefer? Well, I prefer CC to DD. I know you'll come to the same conclusion, so I play C. And you similarly reason that way too, and you play C. So that's how a common culture can make it possible for people to trust each other and end up better off than they would be in the Nash equilibrium. Here are some examples. I've given you this already: recycling, voting, and paying taxes. I gave you those 3 examples. Now let me do a little economic example for you with taxation. We have a set of identical workers. All are earning the same wage. Each has preferences modeled by a utility function, represented by utility function U over consumption and labor. A worker's net income with taxation is 1 minus T times the wage times his labor. Think of this as the real wage. So this is the amount of the good, if there's one good, that he can buy with his labor earnings. But with taxation, each worker also receives what's called a demo grant. They receive 1/n of the total tax revenues back as a check in the mail from the Internal Revenue Service. So this is total income in the society. It's the total wage bill. This is the taxes paid by those workers, and each person gets back 1/n of it. So the utility of the worker is a function of his consumption, which is the first argument here. That's his after-tax income plus his share of the demo grant. LS just means the sum of all the L's. And then, of course, the second argument is his labor supply. So I've just written that again up here. Now, how does a Nash player decide upon his labor supply? Well, he balances his utility from the take-home income against the disutility of labor. So what he does is, I'm going to do a little calculus here. He says, what is the L? Well, there's an L missing here. So what the worker does is he has his take-home income, and then he has his share of the demo grant, and then this is his labor argument. If he holds the other labor contributions fixed, and then he chooses the L that maximizes his utility, the L1, you take the derivative of this with respect to the first argument times the derivative of the first argument with respect to L1, which is just this. Remember, there should be an L1 here. And then plus, the only place that L1 appears is in the first argument here. So when he takes the derivative of this with respect to L1, he gets T over N times W. And then plus the derivative of U with respect to L1, that's just U2. And you can rewrite that in this way. Notice that the sum of these two things is essentially just equal to 1 minus T over W. Suppose N is 1,000,000, and we can just ignore this term. It's going to be very close to 0. So the consequence of this first order condition is that the worker sets what's called his marginal rate of substitution equal to 1 minus T times W. But Pareto efficiency requires that you set the marginal rate of substitution equal to your wage, not your after-tax wage. And the result, so this is not Pareto efficient. Nash optimization with taxation is not Pareto efficient. And the fact that this is smaller than this is called the deadweight loss of taxation. Now, what does the Kantian do? The Kantian says, what's the L I would like all of us to contribute? Well, then my utility would be, this would be my after-tax wage. Now everybody's contributing the same L. So the sum of the L's will just be, the sum of the LI will just be NL. And here I have an L. And if you take the derivative of this with respect to L, notice what you get here. The derivative of this first argument with respect to L is 1 minus TW plus TW. The ends cancel out, and this is just L, so you get that. But what is the sum of these two things? It's W. So we get the formula, which is the condition for Pareto efficiency. So what this shows is, if workers were optimizing in the Kantian manner, then you'd get Pareto efficiency at any tax rate. That's hard to believe. Any tax rate, even a tax rate of 1. All that happens when you change the tax rate is you change the distribution of income, but you don't hurt efficiency. So the Kantian solution is Pareto efficient. It solves the deadweight loss of taxation. Well, the deadweight loss of taxation is just another name for the free rider problem. See here, when people Nash optimize in the labor supply game, they're not taking account of the positive externality of other people's labor for their own consumption. So what happens, just to use this externality language, Kantian optimization internalizes the positive externality of income taxation. Now, what if players have different preferences? Well, all of this generalizes in a fairly sensible way to utility functions that are different across people. The Kantian question becomes more difficult. It becomes more complicated. So I'm not going to go into that here. I think you've covered that with Roemer. I think he's given you some examples. Now today, the biggest negative externality is global warming, created by greenhouse gas emissions. There are about 200 countries. Each country would be better off if all the others reduced their emissions. So it's just like the fishing game. It's a tragedy of the commons. So this is a monotone decreasing game among heterogeneous players, because people have different GDPs, they have a different relationship of carbon emissions to their own consumption in the different countries and so on. It's no longer a symmetric game. The Nash equilibrium leads to huge Pareto inefficiency. We're essentially at a kind of a Nash equilibrium now because there's not much cooperation going on. If this continues, climate problems are going to massively increase. We're going to have wars when people in Bangladesh try to move to India because their country is flooding. There'll be millions or billions of lives lost due to climate change. But the Kantian equilibrium is Pareto efficient. So it would be massively important for people to learn to play that Kantian equilibrium. I view the annual international meetings, what are called the conferences of the parties, as an attempt to create solidarity and trust that are needed to reach the Kantian solution. So let's think of Donald Trump. He's the perfect example of a Nash player. He wants to dissolve all cooperative ventures in which the US is involved. His protocol is belligerently non-cooperative. Think of his slogan, America First. Because of his optimization protocol, the world is now in the most dangerous place it's been since World War II. Learning to cooperate is now a matter of life and death for billions of people. Economic theory can help. Economists should teach their students that Nash equilibrium is not the theory of rationality. Cooperation is another kind of rationality. Having a way to model it will teach us to see cooperation as much more prevalent than we've been taught to believe. Thank you.
I would like to hear from you if you think that what you've heard of Mexican current policies and socialism in general can be consistent with Kantian equilibrium?
Okay, so that's a very good question, very complicated question. I've actually written a long paper, which is called "What Can Socialism Be in the 21st Century?" And it applies Kantian equilibrium to discussing different kinds of property relations that we could have, which would be socialist. The main thing we should be doing now is improving the lives of the disadvantaged in society. Most people are poor due to no fault of their own, and most people who are rich are also rich due to the fact that they had very good luck. Luck in the families they were born into in particular. If you're born into a well-off family, a highly educated family that values education and can give you a lot of resources, probability is you're going to do pretty well in life. If you're born to an uneducated family, people who are very poor, who don't understand the value of education, you're probably not going to do very well in life. So I think that injustice is one of the main things we should care about. My view is there are three pillars on which any economic system stands. One is a set of institutions and property relations. The second is a behavioral ethos, that is to say, a theory of how people should make decisions. And the third is a distributive ethic, that is to say, a moral view of how resources should be distributed, an ethical view. So under capitalism, property relations are what you know. Firms are privately owned by individuals, corporations, and families. And people sell resources on the labor market or on all markets, capital market, labor market, and so on, commodity markets. The behavioral ethos is going it alone. Do the best you can given your own resources and the luck that you were born with. Do the best you can. Don't worry particularly about other people other than your family. So that's going it alone. And that's modeled by Nash equilibrium. Nash equilibrium is a formalization of the behavioral ethos of capitalism. And the distributive ethic of capitalism is it's all right for you to get whatever you can get as long as you don't break the law. Now, what about socialism? The property relations of socialism, there can be many kinds, but they're not going to be, they don't necessarily have to be, let's put it that way, private ownership of firms. Firms can be owned collectively by groups of people. They can be owned by the workers who contribute labor. They can even be owned by the investors also who contribute investment. But there won't be a stock market in that model for becoming an owner of a firm. The only way you'll get a share of the income of the firm is by contributing something to it, labor or investment. So those are the property relations. The behavioral ethos, I say, is cooperation. Rather than going it alone, the behavioral ethos is cooperation. And that's modeled by Kantian equilibrium, by Kantian optimization. And finally, the distributive ethic is, well, equality of opportunity. It's massive equality, deep equality of opportunity, which means that we try to compensate people for bad luck that they have, mainly in the birth lottery, by having institutions that, chiefly education and redistribution, which will insure people against the bad luck of being born in the birth lottery. So very briefly, what I do is I integrate the behavioral ethos into the theory of socialism, and I contrast that with capitalism. And the big story is that you solve all these Pareto inefficiencies that exist under capitalism because of free rider problems and tragedies of the commons. So it's basically just a further articulation of what I've talked about today.
How would the taxation problem change if agents had different incomes?
So if you use linear taxation, but people have different wages because some people are more skilled than others, then you can still get the theorem that you get Pareto efficiency regardless of the tax rate if people Kantian optimize, but you have to use what I call additive Kantian optimization. You don't have a homogeneous society again. You don't have a symmetric game. You have an asymmetric game, and there are basically two kinds of Kantian optimization you can use in an asymmetric game to get Pareto efficiency. One is multiplicative Kantian optimization, the other is additive. So in the taxation problem, if people optimize in the additive Kantian manner, you get Pareto efficiency independent of the tax rate. Now, what does this require in a society? It requires that people think solidaristically, that they're acting in concert with other people. It doesn't actually require you be altruistic. It doesn't, you still evaluate the outcomes from your own viewpoint in terms of your own utility, but you think of acting in concert with other people.
If there are a way to cooperate in something where people think really different in the sense of some people see it as a problem, other people don't.
Okay, it's a good question. Here's the way that you have to think to solve the climate change problem. So suppose that we have a proposal which is an amount of emissions from every country in the world, or every region of the world, say. Say you have 15 regions in the world. And suppose the proposal is on the bargaining table, which proposes how much each region should be allowed to emit in carbon. A multiplicative Kantian equilibrium has the property that nobody, no country or no region would like to rescale that vector of emissions. That's to say, nobody would like to, you can't say, oh, I want to cut my emission, I want to increase my emissions by 10%. You can't say that. You can only propose to increase everybody's emissions by 10%. Or you could propose to decrease everybody's emissions by 10%. Or increase everybody's emissions by 4%, whatever. But the only acceptable proposals are to rescale the whole vector by multiplying it by a constant. If nobody wants to rescale the vector that's been proposed, that's what I call a multiplicative Kantian equilibrium. And if you find such a vector of emissions, which you can always calculate if you know all the technologies of the countries and so on, it's a complicated calculation, but you can calculate that. If no region wants to rescale that vector, it's Pareto efficient, which means it's really about as good as we can do, right? In particular, we will avoid huge climate increases in temperature because that's going to be bad for everybody. So that's the way that you Kantian optimize there. And that takes account of the fact that people have different preferences. So some countries will get to emit more than others, but nobody will want to rescale the whole vector.
If Kantian equilibrium is supposed to make everyone to take E-star action, but given that it's an intertemporal problem, if our grandparents or the previous generations already didn't take the E-star action, does it still hold?
Yeah, making the problem a problem for every generation makes it a much more complicated problem. But suppose you say the citizens of every country care about their descendants and they care about the future, right? So their utility function does not only include their own personal utility, but the utility of their family going down into the future of their descendants. So then the Kantian equilibrium, but they have to make this decision today about how much to emit in the next 10 years, say. To actually do the details of the intergenerational problem is complicated, but the general principle is still there. The general principle is that there will be a vector which nobody will want to rescale, and that vector will bring about Pareto efficiency in the sense that you can't possibly improve every country's utility. But now the utility is not just the utility of the present generation, it's some welfare function of the utility of the present generation and all their descendants.
If there are already differences in income, I just keep thinking of this solution of this Pareto optimal solution that they teach us, where one individual has everything and the other one has nothing. I guess Kantian behavior is not enough.
What you're saying is Pareto efficiency is not the be all and the end all. That's correct. We have to be worried about equity as well as efficiency. So here's one answer to that question. If you have a completely symmetric game, a homogeneous society, then there's no question that the Kantian equilibrium is going to Pareto dominate the Nash equilibrium. It will not only be efficient, but it'll make everybody better off. And that will hold as long as people are fairly close to being heterogeneous. But the more homogeneous, the more heterogeneity you introduce in the population, the less likely it is that everybody will be made better off in the Kantian equilibrium. The Kantian equilibrium will be Pareto efficient, but it might make some people worse off. In the games that we actually consider in real life, you won't have this terrible solution where one person gets everything. But I can't guarantee that everybody will be made better off in the Kantian equilibrium than the Nash equilibrium. But I've done simulations showing that in standard sort of tax models, almost everybody will be better off as long as tax rates aren't really close to 1. If tax rates get really close to 1, then the rich will be worse off than they were in the Nash equilibrium. So typically what happens in real economic problems is that the very richest people will be hurt by Kantian equilibrium. But the benefit is you'll have massive improvements in efficiency. So that's to say most people will be made much better off.
The rich will never want to lose money. So just
right.
cooperative behavior would not
Right.
be enough to redistribute income, right?
That may be so. Like in the tax problem, if you set a tax rate of 95%, that'll make the very, very rich worse off. But the poor will be massively better off than they were before. And in fact, the bottom 95% will be much better off. So I've got simulations of these examples which show what happens with taxation and with redistribution of wealth. But the distribution of wealth we have now and in the kind of capitalism we have today in most countries, including both Mexico and the United States, is so terribly, terribly unequal that if we introduce high taxation, we will, with Kantian optimization, get Pareto efficiency, but the very, very rich will be worse off than they are now. They won't be worse off than the poor, but they'll still be very rich, but they'll be worse off than the poor.
I'm a little skeptic about the trust mechanisms. You spoke about the culture being the trust factor there. But what if the two individuals or the two players cannot find a common ground through which they can build a trust relationship? If the common factor isn't that obvious, like culture, then how can we trust that the other person will want to get to the Kantian equilibrium?
That's right. That's the big problem. And heterogeneity makes it difficult to build trust. But let me give you an example of what's happened in the 20th century in terms of cooperative behavior. If you look at the most highly developed countries in the world, let's say the OECD countries, on average, the government takes about between 30 and 50% of the national income in taxes. And it spends that money on public goods and redistribution through transfer payments. That's a huge form of cooperation. Each country is pooling between 1/3 and 1/2 of its total income to be used for redistribution or for public goods. In the Scandinavian countries and in the Northern European countries, it's about 1/2, about 50% of national income is redistributed through taxation and invested in public goods. That's a huge form of cooperation. That wasn't true in the 19th century because it only came about with income taxation, which began in most countries in the early 20th century. So you have to see that societies have made huge progress in being solidaristic to the extent that they've decided to pool a lot of their income in that way. Now, how did that happen? It happened through democracy. It happened through the extension of the franchise so that ordinary working class people could vote. And when that happened, then people eventually voted to have a lot of redistribution. It also happened because of various catastrophes that occurred during the 20th century, the Great Depression in the 1930s and the Second World War. People came back from the Second World War and they decided they were going to have a more solidaristic society than earlier, and they voted to form welfare states and to increase taxation.
So in the model, you could include things like democracy that make heterogeneity not be like the limit that the model faces.
That's right. That's right. I mean, people have to recognize that although they have a lot of differences between them, they also have a lot of similarities. That's the important thing. It's worth, if you can visit a Scandinavian country, Sweden or Denmark or Norway or Finland, which is a Nordic country, you'll see that the society is much more cooperative and solidaristic than any other country in the world, really. They really have a huge degree of solidarity among their people. And the reason that that happened was that they were fairly heterogeneous with respect to religion, race, language, culture, and it was relatively easy for them to be solidaristic. Now they have a lot of people who've immigrated to those countries. They're no longer as ethnically homogeneous as they were before, but they've still maintained this solidaristic economic policies.
Do you think the current crisis will help people realize that we are all in the same boat and we should be more cooperative?
I can't make any confident predictions about what will happen. Very, very hard to predict. I mean, I thought after the financial crisis in 2008 that people would learn that they have to be solidaristic and they would pass universal health insurance, but they didn't, because the Republicans succeeded in convincing a lot of people that national health insurance would be socialism, and that's a bad thing. So I can't predict what's going to happen. I mean, I'm sorry, but I think there's no guarantee that we're going to get to a better world out of this crisis. I very much hope we will, and a lot of people are talking about that, but it's not clear, it's not necessary that it will happen, it seems to me.